The Weierstrass function is a mathematical paradox. To the naked eye, it looks like a continuous, unbroken line that can be drawn without lifting a pen. Yet, it is infinitely jagged, meaning a smooth slope does not exist at any point. It is continuous everywhere, but differentiable nowhere. In the early 1800s, intuition suggested that if a function was continuous, it had to be smooth at most points. Mathematicians, like André-Marie Ampère, believed that connecting 2 points must involve a smooth line somewhere. They could not imagine a line with corners all the way down, making it non-differentiable everywhere. In the 1820s, Dirichlet introduced a function that equals a constant c for rational x and d for irrational x. This function flips between c and d infinitely often, making it nowhere continuous. While it showed math could be messy, it did not solve the search for a continuous but rough function. In 1861, Bernhard Riemann announced a function he thought was continuous, but nowhere differentiable. However, he never produced a rigorous proof, and later analysis showed his function was differentiable at specific points. This high-profile failure inspired Weierstrass to abandon intuition and construct the true monster. Weierstrass constructed the function in 1872 as an infinite stack of waves, a Fourier series. The amplitude controls the height, which shrinks as n increases. The frequency controls oscillation speed, which gets faster. The key was ensuring the frequency explodes faster than the height shrinks. Building the fractal involves stacking an infinite number of waves. As more terms are added to the summation, the wobbles become infinitely dense. This infinite stacking process is what creates the function that is continuous but non-differentiable everywhere. The continuity of the Weierstrass function is proven using the Weierstrass M-test. The height of the waves shrinks fast enough for the series to converge to a finite value, provided, quote, a is between 0 and 1. This means the sum connects perfectly, ensuring the function is continuous. To prove non-differentiability, we attempt to calculate the slope by differentiating the function. The derivative pulls out the frequency term b to the power of n. For non-differentiability, we compare the shrinking amplitude against the growing frequency. If the product a times b is greater than 1, the slope grows to infinity everywhere. The behavior of the function depends on the parameters a and b. In scenario A, where a times b is less than 1, the waves shrink faster than they tighten, resulting in a smooth function. In scenario B, where a times b is greater than 1, roughness accumulates faster than height diminishes, making it jagged. G.H. Hardy confirmed that a times b greater than or equal to 1 is the boundary for non-differentiability. Karl Weierstrass discovered this function in 1872. Over a century later, in 1975, Benoit Mandelbrot coined the term fractal. The Weierstrass function is an ancestor of fractal geometry, illustrating the key concept of self-similarity. No matter how much you zoom in, the line remains infinitely jagged. Weierstrass expanded the horizon of mathematics by forcing the community to accept pathological functions that defy visual intuition. This video's content draws on several sources, including analyses of the continuity and differentiability proofs, and historical references to Ampère, Dirichlet, and Riemann.